Healthy good evening. Healthy good evening to all of you. This is offline session number 9, ATAL FDP program. Hybrid microgrid opportunity and challenges for renewable energy sources. I am Dr. Shivam, Assistant Professor of Electrical Engineering Department, NIT Kurukshetra, co-coordinator of ATAL FDP program. Heartily welcome Chief Guest of the day, Dr. Rajan Kumar. He is now Assistant Professor in Electrical Engineering Department, NIT Kurukshetra. And coordinator of ATAL FDP, Professor Ratna Dahiya, coordinator of a School of Renewable Energy and Efficiency, Professor in Electrical Engineering Department, NIT Kurukshetra, and faculty members and participants of the event. The primary objectives of the ATAL FDP is to provide a national forum to the faculty and research scholars to share the basic knowledge with an objectives of understanding the concepts, aspect of penetration of renewable energy sources, electric vehicles, and with hybrid microgrid operation. Now, I would like to address of today second session, Dr. Rajan Kumar sir. So he received his BTech degree in electrical and electronics from Chhatrapati Shivaji Institute of Technology, Durg, in 2009. MTech degree from Power Electronics and ASIC design from NIT Allahabad, and PhD degree in Power Electronics, Electrical Machine and Drives from IIT Delhi. He worked with Sukam Power System Limited, Gurugram, India, as a deputy manager. He also worked as assistant professor in Department of Electrical Engineering, NIT Hamirpur, and now he is currently working as assistant professor in Electrical Engineering Department, NIT Kurukshetra. He has awarded as a young scientist by the Department of Science and Technology, DST, Government of India, to participate in the 4th BRICS Young Scientist Conclave held in Rio de Janeiro, Brazil. Dr. Rajan is the recipient of many prestigious awards, including Dr. Rama Murthy West Paper Award at 18th National Power System Conference, NPSC, which is held in Guwahati. Amit Garg Memorial Research Award for High Impact Publication in Quality Journal at IIT Delhi. Best Industry Relevant Project Award at IIT Delhi. And Help Other Program Hope Award at first IEEE Industry Electronic Society Annual Line Conference. He has authored and co-authored several national and international publications. He has also a potential receiver for many reputed professional journals. His current research interest include power electronics converters, electric drives, and solar photovoltaic energy system. So I would like to welcome sir for this session. Thank you, sir. Over to you.
Hello. 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 Hi. Yeah. Good afternoon to all. So the topic of the talk participation is development of solar water pumping system using brushless different device. So assuming that you have enough knowledge of microgrid system, okay, microgrid system is not a new concept nowadays. Everybody knows about it. Only there are so many opportunities and challenges as per the objectives of your course. So what are these challenges? How we can handle these challenges through various technologies. Okay, so this is about one of the most interesting application of solar photovoltaic energy, that is water pumping. That water pumping is actually very important for the countries like India, because we know in India how we get our most of the population depends on the agriculture. Okay, and we know if we use the diesel based water pump or grid connected water pump, that has so many drawbacks. We know there are some limitations of fossil. That's why we are moving towards renewable energy sources. So this topic is especially about the solar water pumping system. So this field, the water pumping system will take energy from the solar panel, and the motor which is used for the water pumping here is brushless DC motor. We will also understand why this brushless DC motor is especially used. Why I have not used any other method. Okay, I will also talk about pros and cons of this brushless DC motor, where we use it for water pumping with solar energy. There are of course some limitations of brushless DC motor also. Right? So we will slowly move by comparing various motors with this BLDC motor. We will see some of the calculation of solar water pumping system using this brushless DC motor. And we will try to understand how we can control this brushless DC motor drive when it is connected to solar photovoltaic panel. Controlling is controlling the speed according to the requirement of water. Requirement of water means amount of water delivery. How much water delivery is required? Let's say for a particular field, right? So why we have chosen this topic? What is the reason? How much government of India is interested in solar water pumping system? Whether government of India is interested or not. So it is very clear example of the interest of government of India. How government of India is continuously promoting the installation of solar water pumps across the country. Government of India is providing a number of subsidies to the Indian farmers, so that Indian farmers can easily install the solar water pumps. So you can see the progress of installation of solar water pumps in the country. So up to 2014, only 11,626 number of solar water pumps were installed. Only 11,000 up to 2014. Okay, and between 2014 to 19, you can see 2.25 lakhs of solar water pumps have been installed, which is 19 times higher solar water pump. Okay, so this shows actually the motivation of government of India. This is again very good example of one of the scheme of government of India, that is called PM Kusum, Pradhan Mantri Kisan Urja Suraksha Evam Uthan Mahabhyam. Okay, in short, it is PM Kusum. So this is very good scheme of government of India for the installation of solar water pumps. You can see the data. How many solar water pumps have been installed across the country in various states under this scheme. Right? So you can see this data up to October 31st, 2019. Okay. This is up to 2019 to 20. So if you see the various states, so the state which is leading in the installation of solar water pumps is Chhattisgarh. 60,430 numbers have been installed so far, and total is 1,81,000 solar water pumps for irrigation in 3 years only under this PM right? Now, this is very important part of this topic. So, this topic will explain why I have used surplus DC motor, why I have not used any other. So, here there are a number of motors which can be used in solar water pumping. Okay, starting from very conventional DC motor, then induction motor, PMSM, that is permanent magnet synchronous motor, BLDC motor, that is brushless DC motor, switch reluctance motor, synchronous reluctance motor. All these motors can be used in solar water pumping. Okay, we will compare this motor and come to the conclusion that why we have used this BLDC motor. So, starting from DC motor, this is actually the conventional DC motor with commutator and brushes. Okay, we know this DC motor, commutator and brushes. So, DC motors were previously used for solar water pumping. Why? Because the input voltage to this DC motor is DC, and output voltage of solar panel is also DC. So it becomes very easy when we connect this DC motor directly with the solar panel. We don't need any power conversion steps in between the solar panel and DC motor. So that was the benefit. That's why these DC motors were frequently used for solar water pumping previously. But problem was this needs frequent maintenance because of commutator and brushes. Okay. Only advantage was one conversion stage is avoided. VSI means voltage source inverter is avoided. Why? Because this is a DC motor. We don't need any voltage source inverter. Okay. So that was the advantage. Disadvantage is commutator and brushes. And you know the efficiency of DC motor, it is always less than 70%. Okay. For full load. If the load is decreased, then efficiency is also continuously decreased. So that is the drawback. We know what is the efficiency of solar panel actually, not more than 20%. So far. Okay. So we have to use a very high efficiency motor so that we can fully utilize solar power. If you use this DC motor which has very low efficiency, solar panel again has very low efficiency. So how much output we will get? We will get very less output. So knowing that the panel has very low efficiency, we should use very highly efficient motor so that we can fully utilize the solar pump, and we can also reduce the total cost of installation of solar panel. So that is about the DC motor. Now coming to the induction motor. This induction motor is very popular. It is very robust. It can be used anywhere. Right? Not only for water pumping, it is most common in various industrial applications. Okay, household applications, right? Railways, defense, many things. So that is more reliable and maintenance free as compared to the DC motor. Okay, suitable for use even in hazardous and contaminated areas. Only problem is the requirement of complex control. This is AC motor. That's why the control requirement is complex as compared to the DC motor. Coming to the efficiency, obviously efficiency of this induction motor is more than the DC motor. We can achieve even more than 85% efficiency with induction motor. Okay. Now PMSM, that is called permanent magnet synchronous motor. So this PMSM is actually the category of synchronous motor. Synchronous motor means what? The motor which can rotate at synchronous speed. 120 into F5P. That is the simple formula. Frequency into 120 divided by number of poles. That is called synchronous speed. If the rotor is able to rotate at that speed, that is called synchronous. So that is PMSM. BLDC is also a synchronous motor because it can also rotate at synchronous speed. But there is difference between PMSM and BLDC motor. The base EMF of this PMSM is generally sinusoidal. But the base EMF of BLDC is not sinusoidal, it is trapezoidal. Okay. So there is very few difference between PMSM and BLDC. PM means permanent magnet. So its rotor has permanent magnet. There is no electromagnetic excitation like induction motor. Induction motor and DC motor has electromagnetic excitation. That's why these motors suffer from electromagnetic loss. Excitation. Okay. But in case of PMSM and BLDC motor, we have permanent magnet in the rotor. Therefore, we can also reduce the excitation loss. That is the reason of high efficiency of PMSM and BLDC motor as compared to induction motor, right? So these uses permanent magnet in the motor. Difference is PMSM has sinusoidal braking effect, BLDC has trapezoidal braking effect. So its usefulness in submersible installation because of its high efficiency as compared to the induction motor. Efficiency of PMSM motor is generally more than even more. Better choice for global efficiency optimization of SPV. SPV is solar photovoltaic fed water pumping. Coming to here, BLDC motor, 15% higher power density than PMSM. So higher power density means size of the BLDC motor will be lower than the PMSM for the same power capacity. Okay, that is called power density. So size of the BLDC will be 15% less as compared to the PMSM for the same power capacity. BLDC motor has high efficiency, as I said. Efficiency wise, BLDC and PMSM are same. Efficiency of these motors are above 92%. Okay, efficiency wise, it has long life, high reliability, low radio frequency interference and noise, and no maintenance. Why? Because this BLDC motor has no commutator, no brushes, like this DC motor. DC motor has commutator and brush. That's why it's called a brushed DC motor. Brushed DC motor. It is called a brushless DC motor because it has no commutator, no brush. Okay, so that's why it is maintenance free. It is maintenance free. SRM, that is called switch reluctance motor. Because of the high efficiency of this four motors, PMSM, BLDC, SRM and FIRM. Okay, because of high efficiency and robust design, this comes under the category of special machines. Okay, these are called special machines because these are designed for high performance with high efficiency, compromising with the cost. Okay, why I am saying that compromising with the cost? Because cost of this BLDC motor and PMSM, SRM, FIRM will be higher than the induction motor. Okay, SRM, switch reluctance motor, a very high torque ripple and acoustic noise problem. So SRM and FIRM, these are actually in research phase for this particular application. Okay, practically we cannot find any application of SRM and FIRM for solar water pump. It is only in paper, in general papers and conferences. So I can say that this motor and this motor are in research phase for solar water pumping application. But we can find practical application of solar water pumping with induction motor, BLDC and DC motor. These three motors we can find in practical application. Ministry of New and Renewable Energy (MNRE). This ministry has recommended induction motor and brushless DC motor for solar water pumping nowadays. So these two are in research phase. That's why it is written that not received much attention for PV array fluid water pump till now. These are only in research papers, right? SYRM, synchronous reluctance motor. Some attempts in the area of PV array fluid water pump using SYRM have been made. This is also not well proven. This is also not well proven. But efficiency wise, all these motors are same. These all are advanced machines, or we can say special machines. Okay. Now, if you compare PMSM and BLDC with this motor, very important difference between this permanent magnet machine and this machine. As I said, this PMSM and BLDC use permanent magnet in their rotor. In India, we don't have permanent. Okay, the permanent magnets are actually imported from China, only available in China. So these PMSM and BLDC cannot be manufactured in India at all. Okay, so if it cannot be manufactured in India, obviously the cost of this motor will be higher. But very interesting thing is we can manufacture SRM and FIRM because this motor doesn't need any permanent magnet. So these motors are just like the induction motor. So we can manufacture induction motor in India, similarly we can manufacture SRM and FIRM in India. That are the advantages of these two motors. That's why You might have heard some applications of SIM and SYM in electric vehicles nowadays. Okay, because we can manufacture this motor in-house. Okay, so in this solar water pumping application, basically we have used brushless DC motor. So we will understand how we can make different configuration of solar water pumping with this brushless DC motor, right? You can see some pictures of this motor also. So this is classification of solar PV. PV means photovoltaic fed BLDC motor driven water pumping system. So how we can make different configurations? How many configurations are possible with BLDC motor for water pumping, solar water pumping? So solar PV fed BLDC motor in water pumping system. This is classified into position sensor based BLDC motor drive and position sensor based BLDC motor drive. Position sensor based means for the speed control we will use position sensor, right? Position sensor based means we will not use position sensor for the speed control. It will be position sensor based. Now the position sensor based control, this is again classified into standalone PV generation and grid connected PV generation. Standalone means simple. We have understood what is microgrid. Similarly, standalone means that will not be connected to the utility grid. Okay, we will have localized generation. We will have some solar panels. Okay, we will generate some power to feed our local load. Maybe some small village, or we can say some small load in a particular house. That is called standalone thing. Okay, there is no connection between our generating system and utility. That is called standalone. Then grid connected PV generation system. Okay, means that system will be connected to the utility grid. Then in standalone PV system also there may be two configurations like double stage PV generation system and single stage PV generation system. Double stage means double and single means this represents actually the number of conversion stages. Double stage means there will be two conversion stages. Single stage means there will be only one conversion stage. There will be a solar panel, there will be a voltage source inverter, and at the output of voltage source inverter, there will be a motor. So only conversion stage, that is voltage source inverter. That is called single stage. In double stage PV generation system, there will be two converters. First, there will be solar panel, then DC to DC converter and voltage source inverter. So there are two converters, DC to DC and DC to AC, that is voltage source inverter. That's why it is called double stage PV generation system. Then in grid connected PV generation system, there will be unidirectional power flow control and bidirectional power flow control. We will see what is unidirectional power flow control and what is bidirectional control. Actually, unidirectional means the PV will generate some power. Okay, we will have some utility grid. We know the PV generation is intermittent; it cannot provide the power at full capacity throughout the day. Okay, it depends on the weather condition. It depends on the available solar radiance, available temperature. Okay, during the morning or during the evening, power generation will be very less. In that case, water delivery will also be very less because power generation is less. So, if I want full water delivery, then what I will do? In that case, what I will do? I will connect my water pumping system with the grid. Okay, and I will take some power from the grid during morning and during evening, so that I can achieve full water delivery throughout the day, even in the night. Okay, so that is called unidirectional power flow. So power will be flowing from grid to the water pumping system. Okay, during the morning, some power will be provided by the solar panel, some power will be provided by the utility grid, and our water pumping system will run at full capacity. That is unidirectional. Means power will flow from solar PV to the motor only. Power cannot flow from PV to the grid. Okay. There sometimes we may feel that we don't need any water pumping. Okay. Then our solar power will be wasted, completely wasted, because we don't need water pumping. So to use the solar panel when water pumping is not required, what we will do? We will transfer the solar power to the utility grid. And that is called bidirectional power flow. Means power can flow from grid to the load. Load here is motor pump is the load here. So power can flow from the grid to the load, as well as grid can take power from the panel. So that's what is called bidirectional power flow control. Now, in double stage PV generation system, we can use DC to DC boost converter, we can use DC to DC buck converter, we can use buck boost converter, or any DC to DC converter available in the market. Generally, these DC to DC converters are used for what? MPPT, maximum power point drive. Right? So these all configurations are also possible with position sensor based belt drive. Okay, these configurations are position sensor based control. These are also possible with position sensor based BLDC motor drive. So the speed control system we are going to discuss is with this position sensor based BLDC motor drive. We will discuss the control of BLDC motor without position sensor, means sensor. So we will first understand here what is the double stage PV generation system, and then what is the single stage PV generation system. Here, this topology is double stage solar PV thread BLDC motor drive for water pumping. We can understand clearly from this topology what is double stage and what is single stage. Here, this is the solar PV panels. Okay, this is the DC-DC boost converter, and this is the three-phase VSI. VSI means voltage source inverter. This voltage source inverter is feeding a brushless DC motor, and this brushless DC motor is coupled with a water pump. Okay, this may be a submersible water pump or surface water. So, how many conversion here? DC to DC 1. This is DC to AC. That's why this is called double stage PV conversion system. This DC-DC boost converter is especially used for maximum power point driving of PV array. That's why it is written here MPPT. ISC, that is incremental conductance. Incremental conductance MPPT. So this is used for MPPT only. And this PSI is used to control the speed of this DC motor. Right. Now for the control, how many sensors we need? Starting from the Hall sensor, these are Hall signals, H1 to H3. That means there are 3 Hall position sensors for the control of BLDC motor. 1, 2, 3. 3 Hall position sensors are there. So we are getting 3 Hall signals from 3 Hall sensors. Including as well as we are also sensing the 3-phase current, ISA, ISB, ISC. These are the 3 currents of 3 different phases. This is the 3-phase BLDC motor. Sometimes we may be confused that why it is called BLDC, because here you can see this BLDC motor is connected at the output of VSI. At the output of voltage source inverter. Output of voltage source inverter is always AC. But name of this motor is brushless DC. So why it is connected at the output of VSI? Why it needs AC power if it is a DC motor? That will be confusing. But actually, this BLDC motor is not a DC motor, it is actually an AC motor. Okay. We are saying this is a DC motor. Why? Because the characteristics of this motor resembles with the characteristics of conventional DC motor, brushed DC motor. That's why we are calling it a brushless DC motor. Otherwise, it is an AC motor, not a DC motor. You can see here, this is 3-phase motor. Okay, this is 3-phase motor. We are sensing this 3 currents, ISA, ISB, ISC. Okay, and this block is BLDC motor control. That means the speed control of BLDC motor. This is the input capacitor of this voltage source motor. So we are also sensing this voltage across capacitor for the speed control. So how many sensors we need actually for the motor control is 1 voltage sensor, these 3 current sensors, and these 3 Hall sensors, Hall position sensors. This number of sensors we need, and using some control logic which is inside this block. Inside this block there is speed control logic. Now we can generate the 6 switching pulses S1 to S6 because there are 6 number of switches in this voltage source inverter. This is 3-phase voltage source. So we can generate 6 switching pulses to operate the switches of these voltage source inverter. Now on the left side, as I said that this DC-DC boost converter is especially used for MPPT. This needs PV array voltage and PV array current. So PV array voltage and PV array current will go to this incremental conductance MPPT algorithm, and this will generate some duty cycle. This duty cycle will be such that this PV panel will always operate at maximum power. Okay? And this duty cycle is actually converted into the switching pulse, and that switching pulse will be used to operate this IGBT of DC-DC boost converter. Okay, so that is actually the two-stage topology. Now, how we can modify this topology? Because this is using this DC-DC boost converter, you can actually calculate the cost involved in this topology: cost of panel, then cost of this DC-DC boost converter, cost of voltage source inverter, cost of VLDC, and cost of water pump, and the cost of this controller. So, what is our objective is how we can reduce the cost of this overall system. Okay, most of the farmers in India are middle class farmers. They cannot afford very high, means very costly system. They cannot afford. Okay, so what the farmers want actually? They want cheap water pumping as well as reliable water pumping. So how we can modify this? So we can eliminate this DC-DC boost converter. If I am able to eliminate this DC-DC boost converter, that will become single stage topology, because this stage will be completely eliminated. So we can eliminate this DC-DC boost converter, right? We can also remove the voltage sensor from this place. We don't need this DC bus voltage. We can also eliminate these 3 Hall position sensor. There is a reason. We can control the speed using this 3 Hall position sensor. But we are trying to eliminate this. Why? Because we know what are the drawbacks of position sensor. Not only in case of VLDC, in case of induction motor also, in case of PMSM, in case of DC motor also. We actually want to eliminate the position sensor. Why? The position sensors are not reliable, and probability of their failure is very high. So if I use the position sensor in submersible water pumping, which is inside the ground, and after 1 year or after 2 years, there is some failure of the position sensor, then what I will do? I have to take out whole water pumping system from inside the earth. So that actually increase the maintenance requirement. That will actually reduce the reliability. That's why we are trying to eliminate the position sensor. These are not reliable. Probability of their failure is very high. The performance of this sensor actually depends on the operating conditions like temperature, right? And this also needs very precise mounting actually on the shaft of the on the stator of the machine. If there is a very small mistake in the mounting of the sensor, that will not give actually the better speed control. That needs very precise mounting, very accurate mounting. There should not be any mistake of 1 degree or 2 degrees. That 1 degree or 2 degrees or 3 degrees of mistake, that will actually deteriorate the performance of speed control. So that's why we are trying to eliminate this position sensor, and we are going for position sensorless approach. Okay, and we can also eliminate this current sensor. Of course, eliminating this current sensor is not actually the recommended solution, because if I eliminate this current sensor, I cannot protect this voltage source inverter from overcurrent or short circuit. But if I want to reduce the cost of overall system, then I can eliminate this current sensor. Voltage sensor is generally more costlier than the current sensor. So this part we can eliminate. Then this system will become single stage. Single stage solar PV grid, sensorless BLDC motor drive for water pumping. So here you can see we have eliminated what? DC-DC boost converter. 3-phase voltage source inverter is only used. which is feeding this brushless DC motor. This brushless DC motor is coupled through this water pump. This is the solar panel. Okay, this is the blocking diode. This blocking diode is used to prevent the flow of reverse current. Okay, this PV panel cannot take the power. It should always generate the power. It should not take the power. But in case of some fault or in case of some abnormal condition, if the current tries to flow from voltage source inverter to the panel, then this blocking diode will prevent the flow of reverse current. Okay, that is the use of this blocking diode. Current will flow from left to right only. It cannot flow from right to left. So in case of single stage PV system, this blocking diode is always used to prevent the flow of reverse current. In case of double stage, this diode is always there with the boost converter. Okay, this will prevent the flow of reverse current. But in case of single stage system, sometimes current will try to flow from right to left. So that's why this blocking diode is used. This is called blocking diode. So here, this voltage source inverter is only used. Then how we will achieve the MPPT now? Because as I said, this DC-DC boost converter was used for the MPPT. Now the challenge is how we will achieve this MPPT with this single voltage source inverter, because voltage source inverter is used for motor control. Now this voltage source inverter has double responsibility. First is motor control, second is MPPT. So this inverter will perform motor control as well as MPPT. Now, how it will perform? Through this logic. This is self-service control of PVA fed BLDC motor driven water pump. So we have also eliminated this all position sensors H1 to H3. But these all signals are actually always required for speed control. Okay. Here we have eliminated, but this H1 to H3 is always required for speed control. So somehow we have to generate this H1 to H3. So how we can generate this H1 to H3? So we are now sensing the line voltages. We are sensing now the line voltages. So we need at least 2 line voltages, and using this line voltages, we can generate these 3 virtual half signals H1 to H3. And from that H1 to H3, we can actually get 6 logics S1 to S6. On the left hand side, we are using this incremental conductance. We can use any MPPT technique. Incremental conductance, perturb observe, anything. So that will give the duty cycle. Then that duty cycle will be converted into the switching pulse. Okay, that will be a single pulse. This side we will have a 6 pulse. Now we will combine this single pulse with the 6 pulse using this AND gate. So we have to use 6 number of AND gates. That's what is written 6 here. So we will use 6 AND gates. That AND gate will be used to combine this pulse and this pulse. Okay, and this output of this AND gate will be the actual switching pulse for this voltage source inverter. So in that way, we can achieve MPPT and motor control through the single voltage source inverter. That is called single stage topology. And advantages, what are the advantages of this topology as compared to this previous topology? So first is this is single stage, or we can say DC to DC converter link PV system for water pump. Okay, so we have eliminated these. So first benefit we are getting is we can reduce the cost of this DC-DC boost converter. Along with that, there will be some losses in this conversion stage, 5% or 6%. That is generally efficiency of DC-DC boost converter is generally 94 to 100%, 94% at max. So there is 5% to 6% loss in this DC-DC boost converter. Now we have eliminated this boost converter. So we can improve the efficiency of overall system. 5 to 6% efficiency we can improve. That is the benefit. So that is the benefit of single stage or DC-DC converterless PV system for water pump. Position sensorless control. These 3 position sensors are eliminated. Okay, so we can improve the reliability of the water pumping system. We can Now go for submersible water pumping because we are using this line voltage sensor. These are also the Hall sensors. These Hall sensors are actually reliable. Okay, we can believe on these sensors. We can go for submersible water pumping. Then reduce the DC bus capacitor. This is the DC bus capacitor in this topology. Here, this is the DC bus capacitor in this topology. So, this voltage source inverter will be operated actually at very high switching frequency, 20 kilohertz, 50 kilohertz, 10 kilohertz. So, when the switching frequency of this inverter is high, the size of this capacitor will be certainly reduced. Because you know the capacitor is inversely proportional to the switching frequency. When the switching frequency is increased, size of capacitor will be reduced. No closed loop for speed control. If you see this, you cannot find any closed loop control. This is actually the open loop control. Okay. So how the speed of the BLDC motor will be controlled because it is open loop now. That is the question. How this will be controlled? So this PV will generate some power, and according to the available power, the speed of BLDC motor will be adjusted. Okay. During the standard test condition, that is 1000 watt per meter square and 25 degrees centigrade, this PV will generate full power. At that time, the speed of the BLDC motor will be at rated speed. Okay, and the water pump will deliver full amount of water. Okay, during morning or during evening, this PV panel will generate less power. In that case, the speed of BLDC motor will be reduced, and the amount of water delivery will also be reduced. Okay, so the speed of this motor will be dependent on the power generated by this PV. It depends on the time. Say, daytime is morning, afternoon, or evening. In that way, speed will be controlled in open loop. There is no closed loop. The salient features of this system is now high efficiency. As I mentioned that the DC-DC boost converter is eliminated here, so we can improve the efficiency. And this BLDC motor also has very high efficiency, more than 92%. So we are using very high efficiency BLDC motor. In that way, we can reduce the size of this PVL. Okay, we can reduce the size of PVL. Let's say if I am using the induction motor in place of this BLDC motor, which has efficiency of 80%. Okay, induction motor has efficiency of 80%. BLDC motor has efficiency of 90%. So it has 10% high efficiency. So for the same amount of water delivery with the BLDC motor, we can use lower size of PV panel because it has more efficiency. Economical. That's why I am saying this system is economical. Why I am saying economical? Because we can reduce the size of PVL. Okay. But on the other hand, the cost of BLDC motor is higher than the induction motor. But the cost is one-time installation cost. But running the water delivery will be continuously more in case of BLDC motor. Reliable for submersible water pumping. Why it is reliable? Because we have eliminated the position sensor. That's why it is now reliable. So for the experimental validation and for the simulation, we have used this specifications of BLDC motor. So power is 1.3 kilowatt. This is the rated power of BLDC motor. Rated speed is 3000 RPM. DC bus voltage is 270 volt. This is rated DC bus voltage of BLDC motor. Number of ports 4, moment of inertia 2.9. Stator current, rated stator current is 4.3 ampere. Voltage constant 68 volt per kilo RPM. Torque constant 0.65 Newton meter per ampere. Resistance 3.5. This is actually the winding resistance, face-to-face resistance. Means this is the resistance of two phases. Similarly, this is face-to-face inductance 9.13 millimeter. This is the face of BLDC. Now we know we have 1.3 kilowatt 3000 RPM BLDC motor, which has the DC bus voltage of 220 volt. This motor we have. Accordingly, we will design our PV array. We don't know how much power of PV panel we need. Right? So we know efficiency of BLDC motor is more than 90%. In between the PVR and BLDC motor, you can say in between this PVR and BLDC motor, there is voltage source inverter, which has the efficiency of around 95% at max. There will be some 5 to 6% loss in this inverter. So we have to take these losses into account. You have to take the loss of this real voltage source inverter. Okay. And by taking the losses of this voltage source inverter and the BLDC motor, we can select a PV array of 1450 watt. Okay, we have considered two losses: loss of BLDC motor and loss of voltage source inverter. Okay, loss of BLDC motor is around 10%. Efficiency 90%, so loss is 10%. Similarly, the efficiency of PSI is 95%, so loss is 5%. So assuming this much loss in the system, we can select a PV array of 1450 watt for 1.3 kilowatt BLDC, means 1300 watt BLDC. So for 1300 watt BLDC motor, we need 1450 watt PV panel. Now this power we need, but how much series panels and how much parallel panels we need, that must be calculated. So 1450 watt is the peak power capacity at maximum power point. Okay, that is peak power capacity. We also know that the DC bus voltage of BLDC motor is 270 volt. Okay, here this voltage is 270 volt, rated voltage, and the input voltage of voltage source inverter is same as the voltage of PV array, right? Because this voltage source inverter is directly connected across this PV array. So this voltage is same. So we can say that the input voltage of this inverter should be the voltage of PV array, that is 270 volt. So that's why we have written here the voltage is 270 volt. So number of series panel will be voltage at MPP divided by voltage of one module. Okay, here we have selected this module which is HD1290. So this module has number of series cells. In module is 36. Maximum power of one module is 90 watt. Open circuit voltage is 21 volt. Short circuit current is 6.4 ampere. Voltage at MPP 17 volt, and current at MPP is maximum power point. This is 5.4 ampere. This is the effect of single module, one module. Okay. So how many series and how many parallel numbers of this module is required? So VMS the voltage of one module. 270 volt is rated voltage. So 270 divided by 17, that is 16. Okay. So 17 is what? This voltage at MPP. Okay. So MPP voltage of this module is 17. That's why we are dividing this 270 by 17. That is actually equal to 16. So that means we need 16 number of modules in series. Okay, this is series module. Number of modules connected in series. 270 by 17 is equal to 6. Similarly, number of modules connected in parallel. That will be 5.37. This 5.37. This is the current rate. Power divided by voltage is the current. So 1450 divided by 270 volt, that is the current, which is around 5.4. Okay. So this 5.37 divided by 5.4. This 5.4 is what? This one. Current at MPP. That means this is the current of one module. So total current divided by current of one module is equal to 1. That means number of modules connected in parallel is 1. Okay. So ultimately what we can conclude is we need 16 number of series modules to get 1450 watt solar array. Then we can calculate the value of the DC bus capacitor also. Here, this capacitor we can calculate. So this is the approach to calculate the DC bus capacitor. A small capacitor connected across the PV array serves as the DC link capacitor of VSI. This is calculated by the ripple current. This IC is what? The current flowing through the capacitor. Okay, why this capacitor is connected? To remove the ripple from the PV array voltage. Okay, that means what is actually assumed, all the current, ripple current should flow through the capacitor. Okay, so IC that is equal to IPV minus IDC. We can apply just a KCL, simple KCL here. Here, at this is the node. At this node we can apply KCL. Okay, so IPV is the incoming current. This current is being divided into two parts. First part is flowing to the capacitor, and second part is going to the voltage source inverter. So IPV will be equal to IC plus IDC. IDC is the current flowing through this line. Okay, just by applying KCL. Okay, so that's why it is written IC is equal to IPV minus IDC. Now IPV is actually the 6.4, which is the short circuit current of PV array. 6.4 ampere, this is the short circuit current. 6.4. That is IPV. Okay, so here in this expression you will put IPV is equal to 6.4 ampere. That is short circuit current of PV array. Is the current supplied by the PV array, and IDC is the DC link current of voltage source. That means this IDC is the input current to the voltage source. The worst condition is presumed, at which IDC is 0. Worst condition is what? PV array will generate only the ripple current. That is the worst condition. Means current whatever is generated by PV array has ripple only. There is no constant DC current. That is the worst condition. The worst condition is presumed at which IDC is 0. So this IDC is 0 here, so IC will become equal to IP. Okay, to estimate the ripple content in the capacitor. So in that case, IC is equal to IC max, that will be equal to IPV, that is 6.4 ampere. And this is very simple formula for the capacitor. We know C is equal to what? Capacitor current is IC is equal to CdV by dt. CdV by dt. So that is the same formula. C is equal to IC divided by FSW. FSW is the switching frequency of voltage source inverter, and this delta VPV. This delta VPV is the permissible voltage in the voltage of PV array. Permissible ripple in the voltage of PV array. So this IC max 6.4. Switching frequency taken here is 5000 Hz. Okay, 336 volt is the open circuit voltage. Okay, here open circuit voltage is 21 volt. Of one module we have connected 17 modules. 17 multiplied by 21. 17 multiplied by 21 is 336. And this 0.02. 0.02 is the means it is 2%. 0.02 is 2%. So we want to allow only 2% ripple on the PV array voltage. That's why we have multiplied this 336 by 0.0. So this will give around 200 microfarad. Okay. So value of this capacitor is adjusted by changing the switching frequency. Right? We can change this. If I increase the switching frequency, let's say it is 10,000. So value will be only 100 microfarad. So in this way we can calculate the capacitor. Now coming to the control part, how we can control the solar PV array, how we can control the speed of BLDC board, so that we can achieve MPPT, maximum power point, as well as the speed control at the same time. So control of single stage solar PV fed sensor based BLDC motor driven water pumping. So how many control logics are involved here? First is INC MPPT, incremental conductance MPPT of solar PV array. This yellow box shows the flowchart of incremental conductance MPPT algorithm. Then electronic commutation of BLDC motor. So this green table actually shows electronic commutation of BLDC motor. We will see what is electronic commutation. Right? In case of conventional DC motor, there is commutation. That is actually the mechanical commutation. In case of conventional DC motor. But in case of BLDC motor, there is a commutator which is electronic commutator, not mechanical commutator. Okay, that actually makes the difference between the efficiency of DC motor and BLDC motor. Whenever there is some electronic system will always have more efficiency as compared to mechanical system. Okay, so here in case of BLDC motor, we have electronic commutator. So this table shows electronic commutator. Then switching pulse. We have this MPPT logic, we have this electronic commutator. And what we have seen that we have to combine these MPPT and electronic commutator using the AND gate. So this MPPT is giving some duty cycle. This duty cycle is converted into the switching pulse. Similarly, this electronic computation will give 6 switching pulses, S1 dash to S6 dash. And these 2 pulses will be combined through this AND logic, this AND gate. Okay, so you can see the frequency of this pulse that will be very high, right? But the frequency of this pulses, this is the S1. Okay, frequency is very less. Frequency is very less. Why? This frequency depends on the speed of motor. 120 F by P. Speed is 120 F by P. If the speed is 3000 and the number of pole is 4, then the frequency will be 100. So this is actually the low frequency signal. But this side, this is high frequency signal. We are going to combine this high frequency signal with the low frequency signal using the AND gate, and this is the final. At the output of AND gate, this is the final PWM pulse, which will go to the switches of voltage source. So this is ultimately the high frequency signal, right? So in this way we can combine these 2 logics, that is called switching pulse generation of PSI. This blue block, okay. And this incremental conductance algorithm is very well known MPPT algorithm, okay, just like pattern and observe MPPT. So this needs the sensing of PV array voltage and PV array current, and ultimately it generates some duty cycle at the output. Sensorless speed control of BLDC motor. So here we have eliminated the position sensor. That's what is called position sensorless speed control. So this is the block diagram of this position sensorless control. How many stages are required? VAB, VBC, VCA. These are the line voltages. We are sensing this line voltages, right? And there are several stages like pre-positioning, starting, and running. Sensorless running, sensorless starting. Okay, so this sensorless technique is actually based on the zero crossing of back EMF. So we are trying to identify the zero crossings of back EMF of BLDC motor. As I said that the back EMF of BLDC motors are trapezoidal, not sinusoidal. So this trapezoidal back EMF will have some zero crossing, and we will try to identify that zero crossing. And based on that zero crossing, we will generate the Hall signal, virtual Hall signal. And we know this back EMF actually depends on speed. Back EMF is directly proportional to speed, just like the conventional DC motor. EB proportional to speed. Omega. EB proportional to omega. So just assume the starting condition at standstill speed of the motor is 0. So back EMF will also be 0. Okay, so back EMF is 0. So how we can identify the zero crossing if it is 0? So at starting, this sensorless algorithm is not successful. This cannot detect the zero crossing. This cannot sense the speed. So that's why there is another additional stage that is called the pre-positioning. So at standstill at very low speed, back EMF zero crossing is not detectable. That's why we go for pre-positioning. Right? So we'll understand what is pre-positioning. And these block diagrams are actually for running. There are 3 modes: pre-positioning, starting, and running. This block diagram is for running. So the first block is line voltage to back EMF. When we say back EMF are internal signals. These are not external signals. We can access the output voltage. It means we can access the phase voltages, but we cannot access the back EMF. These are internal signals. Back EMF is phase to neutral voltage. Okay, we have let's say we have terminal A, and the voltage with respect to terminal A and neutral, that is breakeven. So we don't have neutral terminal. We have only 3 wires. Phase A, phase B, and phase C. We don't have neutral wire anymore. It is not accessible. So how we can access the back EMF? We cannot access the back EMF. So what we will do? We will sense the line voltages and we will try to convert these line voltages into back EMF. Okay. So this logic is actually based on the zero crossing of back EMF. Means you will detect the zero crossing of back EMF and how we will generate back EMF through the line voltage. So first stage is the line voltages to back EMF conversion. We will convert these line voltages into back EMF. So we are sensing VAB, VBC, and VCA. These 3 voltages will be converted into EAN, EBN, ECN. These are the 3 back EMFs now. Using some mathematical derivation, we will convert these line voltages into these back EMFs. Okay. Now, let's see this. This is actually the detailed block diagram. We will come to that. Before that, let's understand what is electronic commutation of DC. Okay, this table. What is electronic commutation? So, in simple language, what is commutation? We have studied the simple for electronic switches like resistor. Okay, what is commutation? Commutation is turning off. Okay, turning off of the device is called commutation. In simple. So, if you let's see this diagram, this one. If I turn on or turn off any of these switches, then what happens? Current will be shifted from one phase to another phase. Okay. If I turn off this one, current will not flow from this phase A. Okay. So commutation means shifting of current from one phase to another phase. How? By turning on and turning off of this switch. That is actually the commutation. This table. And on what basis we will turn on and turn off this switch? That will be logically operated so that we can accelerate the motor and we can achieve the maximum torque from the motor. We cannot randomly turn on and randomly turn off. Otherwise, motor will not be accelerated. Right? It will make some noise. So that is actually the logical operation. So how it is operated? The first column shows the rotor position, angular position. In degrees, 0 to 60 degrees, 60 degree to 120, like that, up to 360 degrees. This is the angular position of the rotor. Then, these are the Hall signals, H3, H2, and H1. We know 3 Hall sensors are generally connected. Okay, to detect the Hall signals. So these are the 3 Hall signals. And these are the 6 switching signals, S1 to S6. Means these are the states. 1 means on state, 0 means off state. These are the states of switches of voltage or change motor. So following the rotor position, the Hall sensors provide 3 Hall effect signals on 60 degree span. You can see 0 to 60 degree, 60 to 120 degree. So in 60 degree span, there will be some sequence of Hall signals. Let's say for 60 degree to 120 degree, 0, 0, 1 means this sequence of S3 is 0, S2 is 0, and H1 is 1. Means H1 is high, H2 and H3 are low high. So the Hall sensor will provide 3 Hall effect signals, and these Hall effect signals are logically converted into 6 switching pulses used to operate the voltage sourcing motor. So for 60 degree to 120 degree, 0, 0, 1, and switch S1 and S6 will be turned on. Other 4 switches will be turned on. Similarly, for 300 to 360 degree, sequence of Hall signal will be 1, 0, 0, and S4 and S5 will be turned on. So you see this one. S1 and S4 will be turned on. S3 and S6 will be turned on. So very important point is the 2 switches of the same leg will never be turned on. We will not turn on S1 and S2 simultaneously. Otherwise, there will be a short circuit of the DC bulb. Okay. So 2 switches of the same leg will never be turned on. And here the one switch will be conducted for 120 degree. Okay, one switch will be conducted for 120. Means this inverter will be operated in 120-degree operating mode. There are two modes of operation of three-phase voltage of the inverter, that is 180-degree and 120. So this inverter will be operated in 120-degree mode because each switch will conduct for 120 degree. Right? So these are the logical steps. So this table must be followed for the proper operation, proper acceleration of the BLDC. Okay, means after 180 degree there will be 240 degree. After 011 there must be 010. After that there must be 110. So this table must be followed for the BLDC model. That is actually called electronic computer. And when we follow this table, that will give good acceleration to the motor. That will give the required amount of torque. Now we will understand this block diagram. Here, through this mathematical expression, we are converting this line voltages to the wave EMF. These are the mathematical expressions. So we can see from this mathematical expression that there is a relation between line voltages and wave EMF. Like EAN, that is equal to VAB minus VCA divided by 2. Right? So we can convert this line voltages into wave EMF. EAN, EBN, and ECN. That is called line voltage to wave EMF converter. Now, what are the use of these stages now? Why we are using low pass filter? Why we are using this stage rate compensator? Okay. So we will understand one by one. These are the derivations actually. How you can derive the relation between line voltages and wave EMF. You can see these three equations 9, 10, and 11. So EBN, that is the wave EMF of phase B, is equal to VBC minus VAB divided by 2. Similarly, EAN, that is wave EMF of phase A, is equal to VAB minus VCA by 2. And wave EMF of phase C is VCA minus VBC divided by 2. So it is obvious from the above expression that the wave EMFs can be easily estimated using the line voltage. But what is the problem now? These are the waveforms of the line voltages which are actually generated from the these are the wave EMF of wave EMFs which are generated using the line voltages. Our ultimate objective is to detect the zero crossing of the wave EMF. But here you can see at which point there is zero crossing. There are multiple zero crossings. This is phase A, phase B, and phase C. If you see for phase A, this is also the zero crossing. This is also the zero crossing. In one cycle, you can see how many zero crossings. 1, 2, 3, 4. So this number of zero crossings are there. So the waveforms of this estimated wave EMFs contain spikes due to freewheeling diode conduction. You can see this is spike, this is spike, this is spike, this is spike. These are due to the conduction of freewheeling diode. Where are these freewheeling diodes? These are the freewheeling diodes. This diode, this diode. Okay. So when the switch is off, this freewheeling diode conducts. And during the conduction of this freewheeling diode, we will get these spikes. This is spikes we will get. Okay, but the desired zero crossing is this one. This one is the desired zero crossing. Okay, this is the desired zero crossing. This is not desired. This is due to this spike. This is also due to this spike. This is not desired. So we have to remove this undesired zero crossing. This unwanted zero crossing we have to remove. So how we will remove this unwanted zero crossing? They will use the low pass filter. Okay. These are the transfer functions for low pass filter. Omega C divided by S plus omega C. So when we use this low pass filter, we can eliminate the unwanted zero crossing. So EAF, EBF, ECF. These are the filtered wave EMF. Okay, these are the transfer functions of our low pass filter. So the cutoff frequency of the low pass filter is determined on 2500 radian per second by considering both the phase shift and unwanted zero crossing. The transfer function of the low pass filter is this one. For the rated speed of 3000 rpm, we have selected this transfer function. 2500 is what? Cutoff frequency in radian per second. right? What happens when we increase the cutoff frequency? And what happens when we decrease the cutoff frequency? So when we decrease the cutoff frequency from 2500, let's say 1000, then the phase delay will be increased. That is actually the characteristics of filter, any low pass filter. Right? When we decrease the cutoff frequency, that will increase the phase delay. Okay? And when we increase the cutoff frequency, let's say from 2500 to 25,000, then what happens? There we may allow some of the unwanted spikes. Right? Some of the unwanted spikes may not be filtered. So that should be properly chosen actually. So as I said that by using the low pass filter, when we use low pass filter, that will cause the phase delay in the signal. So to eliminate that phase delay, we are using the phase shift compensator. Right? We can see the experimental results here. We have used this low pass filter. Now you see, this is for the design of phase delay compensator. This is the stator current of BLDC, ISA, stator current of phase A. This is S1, S1F. So you can see the delay in switching signal. Delay in switching signal. How much delay we are getting? We are getting 9.8 degree. 9.8 degree of delay we are getting because of low pass filter. Right? This is the desired one, S1 reference. This is the desired, but we are getting this S1 dash, S1 dash, S1F dash, which is actually 9.88% phase difference. But if you go with this 9.8 degree phase difference, that will cause very high noise in the BLDC motor. We will not achieve the desired torque, whatever is required. That's why we cannot go ahead with this 9.8 degree. We have to anyhow reduce this 9.8 degree delay in the switching signal. So that's why we have connected this block, which is called phase shift compensator. This phase shift compensator will help to reduce the phase delay in the back EMF. These are the transfer functions of phase shift compensator. Okay, this is the transfer function of phase shift compensator. K S plus omega C1 divided by S plus omega C2. Being a 4-pole, this is the specification of our BLDC motor. 4-pole BLDC motor, 3000 RPM. Fundamental frequency is 100 Hz. Okay. In radian, it is 628.32 radians per second. Therefore, it is indicated that a phase delay of 9.8 degrees. We have seen here in the experimental result, 9.8 degree of phase delay. So, theta D, that is the delay here, is 9.8 degrees, that occurs at 628. So, these results are at rated speed, 3000 RPM. Okay, this motor is running at 3000 RPM and their delay is 9.8 degrees. When we reduce the rotating speed, that delay angle is also reduced. So, this is the highest delay angle because we cannot run the motor above 3000 RPM because it is the rated speed. So, this is actually the worst condition, 9.8 degrees. That's why this is designed at 9.8 degrees. So, the constant K is 1 plus theta D divided by 1 minus theta D. Theta D is delay at 9.8 degrees. So, it is 1.41. 1 plus sin 9.8 divided by 1 minus sin 9.8. The formula for the time constant is 1 by omega under root K. 1 by omega frequency in radian per second 628.32 under root 1.41. So this is 1.3 into 10 to the power minus 3. And formula for omega C1 and omega C2. This crossover frequencies omega C1, omega C2. This depends on the time constant 1 by KT. So we will get 545 radian per second. Omega C2 is 746.5. Okay, we can put these values and we will get this transfer function for the phase rate compensator. 1.41 S plus 529 divided by S plus 746. We will connect this phase rate compensator and we can reduce the phase delay up to 2.7 degrees. right? We can reduce to up to this. Now this 2.7 degrees is acceptable. Practically we cannot achieve 0 SDG. That is ideal condition. So this 2.7 degree is actually acceptable SDG. From 9.8 degree, we have now got only 2.7 degree. So we can go ahead with this phase delay. You can now see the phase delay is reduced. At last, generation of computational signals. You can see here also this point. After the phase rate compensator, ECP, EAP, EBP. So this ECP, EAP, and EBP, these are the back EMFs, means compensated back EMFs. Okay, these compensated back EMFs are used to generate the computational signals ZA, ZB, ZC. These are actually the three virtual Hall signals. This ZA, ZB, and ZC. These are equivalent to three virtual Hall signals. Okay, so through the comparator, we can generate these three signals, and through these three signals, we can generate the 6 switching pulses using this logic gates. These are the logical operations. So ultimately, we have generated the 6 switching pulses using the 3 line voltages. These are the comparators ZA, ZB, ZC, and then using this ZA, ZB, ZC, there are 6 switches S1, S2, S3, S4, S5, and S6. So these are the logic gates. Okay, logical operations. But for this logical operations, we don't need any hardware. We can set these logical operations inside the our DSP, digital signal processor. We don't need any external hardware. That is the part of software. Now, one thing we have left here is this prepositioning and starting. Okay, these blocks are for running operation, sensorless running. But at steady state or at very low speed, there is no back EMF. So how we can detect zero crossing? That is the filter. So at steady state, what we do? We do pre-positioning. Pre-positioning is also called the rotor alignment. Okay. So how we align the rotor? We randomly turn on the 2 switches according to this table. Let's say S2 days and S3 days. 1. Sorry. S2 days and S3 days. 1. We will turn on S2 and S3 randomly. We can turn on any 2 switches. Okay. And what this will do? When we turn on S2 days and S3 days, rotor will accelerate and it will lock at 60 degrees automatically. Because this switching sequence is for 60 degrees. So rotor will be locked at some position. We don't know what is that angular position. And we don't need the idea of that position. We will just turn on the 2 switches randomly and rotor will accelerate and it will be locked at one position. It will not rotate. It will accelerate and it will be locked at one position. Right? Now what we will do? We will apply the next switching step. Initially we applied S2 days and S3. Next sequence is S2 days and S5 days. Okay, so we will turn on S2 and S5. So rotor will further accelerate and it will go to next angular position. Then we will apply next switching step. In that way, rotor will accelerate. Okay. So that is called a pre-positioning. First step is called a pre-positioning when we operate 2 switches S2 days and S3 days. Okay. When we turn on S2 days and S3 days, means S2 is connected at phase B, S3 is connected at SC. So phase B and phase C will be energized. Okay, only 2 phases will be energized randomly. Okay, so by energizing any 2 phases randomly, the rotor will be locked at particular position, that is called pre-positioning. One more thing we have to remember is when the back EMF is 0, current will be very high. Current is what? When, if you remember the back EMF equation, this is the back EMF equation and this is true for DC motor also, simple DC. V is equal to RAIA plus back EMF. It is the back EMF equation. DC voltage is RAIA plus back EMF. This LS dA by dt will be 0 under steady state. Okay, this LS di by dt is what? Voltage across the inductor. The voltage across the inductor is 0 under steady state. So we will have only VA is equal to RAIA plus EA. This is called a back EMF equation. But at standstill what happens? Speed is 0, so this back EMF is also 0. So only remaining term is VA is equal to RAIA, and IA will be voltage divided by resistance. So actually at steady state back EMF is 0. That's why current is very high. Okay, current is very high, and that current may damage the stator winding. That is dangerous actually. That is not acceptable. So we have to take care of the starting current also during pre-positioning. Here, during pre-positioning, we have to take care of the starting current because back EMF is 0, current may be very high. So how we can take care? We can control the duty cycle of the switches of voltage sourcing. Okay, so when the duty cycle of the switches is very less, that will not allow the current to go beyond the acceptable value. That current will be controlled within the safe limit. Okay, and when we apply the next switching state, that is called a starting. Okay, first it is pre-positioning. When we turn on the two switches, and when we turn on the next switches, that will be called starting. And motor will be accelerated slowly. Okay, once the motor achieves some speed, let's say 500 RPM or 600 RPM, at that speed, some back EMF will be developed because back EMF is proportional to speed. Some back EMF is developed means we can now identify, we can detect the zero crossings of that back. Okay, and once the back EMF zero crossing is detectable, we can apply this sensorless running load. Okay. So this is actually the simulation model of that topology which I have shown. You can see the solar PVL. This is the model of solar PVL. This is the three-phase voltage source motor. This is the AC link voltage. Okay, and this is the BLDC motor. Okay, this block is estimation of back EMF from line voltages. You can see this phase A, phase B, and phase. Estimation of back EMF, then low pass filter, then phase shift compensator. Okay, then computation signal generator, then generating signal, getting signal generator. So ultimately we are getting S1 to S6. That S1 to S6 is combined using this AND gate, and this S is coming from this MPPT. This is coming from this MPPT. This is incremental conductance MPPT, which needs PVRA voltage and PVRA current. Okay, at the output of MPPT, this duty cycle is generated. Okay, this is the duty cycle. And that duty cycle is actually converted into the switching pulse, this S. This S is here. We have combined this S and this S1 to S6 using this AND gate. And this pulse will operate the voltage sourcing. In that way, we can operate this BLDC motor. We can run this BLDC motor. And this block shows the characteristics of water pump. Okay, this is loaded like that. This is the input cover. Now, this insulation level of radiation may be changed. Okay, you can see this result. This result, this S is watt per meter square. Means this is insulation level or irradiance. This is 1000. 1000 is what standard test condition. It is not practically, you cannot achieve this standard test condition practically. Then this is PVRA voltage VPV. This is IPV, that is PVRA current, and this is PVRA power PPV. So when the solar radiation is 1000 watt per meter square, you can see MPPT will start working initially. Okay, it will try to track maximum power of solar PVRA. So at this point, the MPPT is able to track, the MPPT logarithm is able to track the maximum power point. So it will start from open circuit voltage. This point is what? Open circuit voltage 336 volt. Slowly it will be reduced and it will come to 270 volt. 270 volt is what? VMPP voltage. We have seen these specs. This is IPV, current solar PVRA current. This solar PVRA current is slowly increasing. And power, which is the multiplication of voltage and current, this will slowly increase, and this will reach the maximum power point. This is maximum power point. And this jerk, you can see this jerk. Okay, there is a difference between the inertia of the motor system and converter system. Okay, there is difference between the time constant. Power electronics converter has some time constant, motor has some inertia. Inertia of the motors are generally higher. Motor is what mechanical system, but power electronics, these are the electronic system. The electronic system has less time constant. So it is very difficult to match the time constant of electronic system and inertia of the motor. That's why it is taking some time to achieve the MPPT. That's why we are getting this from here to here. This is actually the searching phenomena. This is searching for maximum power point. But ultimately we have achieved maximum power point. Maximum power was how much? 1450 watt. So this is 1450 watt. This current is 5.4 ampere and this voltage is 270. So this is showing starting and steady state performance. This is starting and this is steady state. 8,000 watt per meter square. So these are for PV array, okay, and these are for motor. EA, EB, EC. So these are the back EMFs, estimated back EMFs, ISA, ISB, IST. So phase A stator current, phase B stator current, and phase C stator current. N, that is the speed of BLDC motor. TE, that is electromagnetic torque of BLDC motor. And TL is the load torque, that is the torque of water pump, that is the load. So you can see it is starting, back EMF is very, it is zero. Okay, because back EMF is zero, it is starting because the speed is zero. You can see the speed is this speed is zero initially. Okay, that's why back EMF is zero. So from here to here, this is actually the pre-positioning. You can see motor is accelerated from zero speed to some speed. Okay, and it has again come to zero because motor will be locked at some position, means speed will be again zero. So you can see speed is zero from here to here. Now we have applied a starting algorithm, means we have turned on the next switches. So motor will try to accelerate. You can see motor is now accelerating up to this point. Okay, at this point. And at this point you can see we have got sufficient back EMF, EA, EB, AC. We have got sufficient back EMF and we can easily detect the zero crossings of this back EMF. Okay, at this point. So at this point we have now applied the sensorless running mode. Okay, the third mode, and this motor is running in sensorless mode. Okay, and you can also see the stator current. At a time, only two switches will be turned on, as I said. So you can see some current is flowing in phase A, current is flowing in phase B, but phase C current is zero. Because at a time only two switches will be turned on, means only two phases will be energized. So here phase A current is positive, phase B current is negative, and phase C current is zero. And during starting, these stator currents are actually controlled so that it should not go beyond the acceptable limit. So motor current is controlled. And from here to here, this is starting mode. Up to this point, this is pre-positioning. Up to this point, this is starting, and after this point, it's the running. There are three modes of operation. And these are the steady state waveforms, and these are for running mode of this. Back EMF, you can see this is trapezoidal, as I have already mentioned. The back EMF is trapezoidal. Phase A, phase B, and phase C. This is stator current, phase A, phase B, and phase C. So ideally, the stator currents are quasi square waveform. This speed is 3000 RPM. That means motor is running at rated speed because we have applied 1000 watt per meter square. That is the standard condition. That's why motor has attained its full speed 3000 RPM. Similarly, the electromagnetic torque is 4.2 Newton meter. Sorry, 3.2 Newton meter. The rated torque. This is load torque. So load torque must be equal to the electromagnetic torque for the stable operation. That will be. So these are starting and steady state performance for 1000 watt per meter square, and all these parameters belong to PFDC mode. And this is under dynamic operation. Means solar radiation is changing from 1000 to, you can see, 200 watt per meter square, and again it is increased to 500 watt per meter. Initially radiation is 1000, after that it is 200, and again it is 500. So it is dynamically changing. So under varying weather condition, the voltage is also varying. Okay, this is the PV array voltage. Okay, and this is the PV array current. Initially it is at 5.4, and then PV current is reduced because the radiation is reduced. So it is reduced, and when the radiation is again increased, PV current is increased. Accordingly, PV array power is also changing. Initially it is 1.45 kilowatt. Now it is reduced, and again it is increased. And motor, BLDC motor will follow this variation in PV array parameter. So you can see this is the BLDC motor variable. These are following this change in the solar PV array indicator. You can see this behavior is now reducing. This is with this initially it is with respect to 1000. Now it is 200. It is 500 radiation. Then this is stator current. It is 1000 watt per meter square. This is 200 watt per meter square. And this is 500 watt per meter square. ISA, ISB, ISP. Similarly, the speed is 3000 RPM. Now speed is reduced. Then speed is again increased. So this is actually following the variation in weather condition. Then you can see electromagnetic torque is also varying. Similarly, this load torque is also varying. So the system which is developed is actually showing the stable operation under the variation PV array parameter. Okay. Now this performance is also validated through the experimental setup. Okay, this all are simulation results. Now we have demonstrated the performance through the experimental validation also. So for that, you can see these are the wires from solar PV system. We have a programmable DC power supply, and that programmable DC power supply is providing the characteristics of actual solar panel. So these two wires, are coming from the solar panel, solar simulator system. These are not the actual panel. These are the programmable power supply which is giving the characteristics of solar panel. Okay, and this is, you can see, this is BLDC motor. This is small BLDC motor of 1.3 kilowatt, and this is the DC generator which is coupled through this DC. Okay, and this DC generator is supplying this resistive load. Okay, this DC generator is supplying this resistive load. And on the left hand side, you can see this is the DSO, digital storage oscilloscope, to record the waveforms. Okay. Then this is the sensor board. You can see these are the voltage sensor and current. This blue one, voltage sensor and current sensor. Okay. And this is voltage source inverter, three-phase voltage source inverter. Okay, VSI. This is computer system, and this is DC power supply, auxiliary supply to provide the supply to the sensors and the driver circuit. Okay. Then this is, you can see, MCB. This is fuse. This is isolation circuit. Okay, optocoupler circuit. And this is your P-space 1104. This is used to actually generate the control element. MPPT control and motor speed control. So motor control and MPPT control, these are developed through this P-space 1104 control, real-time control. And this real-time controller is interfaced through this computer system. So this is actually the hardware setup or the demonstration. Okay. Now these are the recorded waveforms. You can see this is the PV array characteristic. Okay. This green one is IV characteristic, and red one is PV characteristic. Power versus voltage characteristic, and the green one is current versus voltage. voltage characteristic. And this is actually showing the MPPT performance. This is showing MPPT percentage, how much MPPT we have achieved. So first one, this is with respect to 1000 watt per meter square, and second one is when the radiation is 200 watt per meter square. So you can see this point. This point represents the operating point. Okay, and you can see this operating point is exactly at the maximum power point. That means we can say that our MPPT algorithm is operating the solar panel at maximum power point. Means it is able to extract the maximum power from the solar panel. And efficiency of MPPT you can see more than 99%. Okay, more than 99%. Similarly, for 200 watt per meter square, you can see power is here, which is 270 watt. Sorry, almost 300 watt. This is the power. So almost 300 watt, and this is the operating point. So efficiency is, in this case also efficiency is more than 99.6%. Here it is almost 100% for 1000 watt per meter square. For 200 watt per meter square, it is more than 99.6%. So under various insolation level, our algorithm is able to achieve maximum power point. These are the experimental results. So first you see, first one is PPV, that is PV array power. Second is ISA, that is stator current of phase A. Third is speed M. Okay, so you can see this PV array power is increasing from 0, and at this point it is maximum, that is 1450 watt. And this jump is again, actually this is the surging phenomenon from here to here. And this is stator current. This is stator current from here to here. You can see stator current is constant. Why? Because this is pre-positioning stage. Okay, rotor will be locked into one position, so current is constant. And this current is actually controlled so that it should not exceed the acceptable value. Okay, how it is controlled? By controlling the duty cycle of the inverter. So from here to here, this is pre-positioning, and from here to here, this is starting. So at the starting, you can see the motor current is somewhat higher. Okay, but this is acceptable. This somewhat higher value is acceptable. During running, you can see motor current is at rated. So this is motor current of phase A, and the speed you can see speed is increasing, and ultimately it has reached 3000 RPM. Okay, scale is 2 kilo RPM per division, so it is 3000 RPM. And this first one is VPV, that is voltage of PV array. Okay, voltage of PV has increased and it is 270 volt. At 1000 watt. All the results are for 1 kilowatt per meter square. So voltage is 270 volts. Okay, current is 5.4 ampere, and this PV array power is 1450 watt. So this power are same. These are the three phase currents: phase A, phase B, and phase C. So here you can clearly identify the stator current is constant up to this point. This is pre-positioning. Okay, this is pre-positioning. And you can also observe that phase A current is positive, phase B current is negative, and phase C current is 0. So at a time, only two switches will be operated and only two phases will be energized. So this point, up to this point, this is pre-positioning, and up to this point, this is starting. Then it is now running. Fourth one, this is EAN, EBN, ECN. Means what? These are the estimated wake signals. Estimated wake. So these are actually the internal signals. Estimated wake signals. Then again, these are the steady state results. VPV constant 270 volt, IPV constant 5.4 ampere, and this is the duty cycle which is generated through the MPPT algorithm. So it is almost 1. This is PPV, PV array power, ISA, that is the stator current. The stator current is quasi square wave. You can see this quasi square wave. Ideally it is quasi square, but because of the prevailing diode, it is not exactly quasi square. Okay, you can see this rise and fall of the current. Okay, this is rising and falling. Similarly, rising and falling. This is because of prevailing diode conduction. Then this is S1. S1 is the switching signal for switch 1. And you can see efficiency, frequency of this S1 is very low. So it is 100 Hz only. Okay, fundamental frequency 100 Hz. And this is the speed. Port 1 is the speed 3000 RPM. Okay, and these are three currents: phase A, phase B, and phase C. You can see the phase difference is 120 degree because DC motor is the star connected load. This is star connected load. Phase difference between the three currents will be 120 degree. You can see this 120 degree phase difference between the three currents. And if you calculate the RMS value of these three currents, this will be 4.3 ampere. That 4.3 ampere is the rated current of the. And these are EAN, EBN, EB, ECN. So these are actually the filtered wave cables. Now these are the experimental results at 200 watt per meter square. Okay, so this setup is actually tested for standard condition as well as the lower radiation up to 200 watt per meter square. So up to 200 watt per meter square, this will run successfully. Means it will deliver the water successfully. So this is PV array voltage. Okay, this is PV array current, which is almost 2 ampere, and this is the duty cycle. So duty cycle now it is around 0.7. In previous case, duty cycle was 1. At 1000 radiation, it was 1. At 200 radiation, it is less than 1. It is 0.7. This is PV array power, which is 300 watt. We have seen here also around 300. This is for 200 watt per meter square. So it is around 300 watt. Okay. So that 300 watt, here it is around 300 watt. Okay. Now this is the stator current. Okay. The stator current is now reduced. Similarly, this 420 speed is also reduced. It is around 1200 RPM. Why? Because radiation is reduced, so PV array is not giving full power. Okay, that's why this speed is reduced. This third one is actually S1. Difference you can find here, in case of 1000 watt per meter square, this frequency of this switching signal is only 100 Hz, fundamental frequency. Okay, but here in case of 200 watt per meter square, you can see this high frequency switching component here. Why? Because we are combining the signals with the duty cycle. In case of 1000 watt per meter square, duty cycle is 1. Okay, so when we generate some switching pulse with the duty cycle 1, what you will get at the output? Always 1. Okay, here at the end logic. Here, if the duty cycle is 1, let's say. So when you compare this 1, the high frequency signal, what you will get? Always 1. At the output of this comparator, you will get 1. So we are combining this 1 with this signal. So at the output of AND gate, what you will get? This signal. So that's why at the output of the AND gate, the frequency of signal is low frequency, 100 Hz. When the D2 ratio is 1. But when the D2 ratio is not 1, when it is less than 1, let's say 0.7, and when this 0.7 is compared with this high frequency signal, there will be some high frequency signal at the output of this comparator. Okay, and that high frequency signal will be combined with this low frequency signal. So at the output of AND gate, we will get this high frequency. So only at the duty cycle of 1, we will get low frequency output of the AND gate. Okay, and below duty cycle 1, we will get high frequency signal output from AND gate. Okay, so at 200 watt per meter square, duty cycle is less than 1. If you see, this is the case of 200 watt per meter square, and duty cycle is 0.7. Okay, the scale is 0.5 per division, so it is 0.7, around 0.7. So we will get some high frequency signal from the comparator, and ultimately at the output of AND gate, we will get this high frequency component. And that high frequency component is also reflected on the stator current. You can see these are the high frequency component. In previous case, you can see there is no high frequency component. It is only fundamental component. But here, this high frequency component is reflected on the stator current also. These are the dynamic operations. So what we have considered is solar radiation is increasing from 600 watts per meter square to 900 watts per meter square. Right? So initially, this PV array power is corresponding to 600 watts per meter square. Now it is increased. When the PV array power is increased, this stator current is also increased, and correspondingly, the speed of the motor is also increased. Okay, this you can see. And these are the three phase currents: ISA, ISB, and ISC. All the currents are increasing when the solar radiation is increasing from 600 to 900. So motor is actually following the behavior of solar array. This is the reverse case. Now the radiation is decreasing from 900 watt per meter square to 600 watt per meter square. So initially, this PV array power is corresponding to 900 watt per meter square, and now it is decreasing slowly. Okay, and ultimately, this PV array power is corresponding to 600 watt. This is stator current, which is also decreasing, and this last one is speed, this is also decreasing. Right? And this three are stator current, these stator currents are also decreasing because solar radiation is decreasing, so solar array is not providing full power. So these all are experimental results. So these are some cost analysis you can see. Overall cost of the proposed system, you can see proposed one is blue one, this last one. So this first one is the cost of PV array. Okay, then cost of intermediate converter. In case of this topology, it will be zero because we have eliminated boost converter. So there will be no cost of intermediate converter. Then there will be cost of voltage source inverter. Then the cost of our control control system, which includes the microprocessor, okay, and voltage sensor and current. Then the cost of motor pump, okay, and the total cost you can see it will be around 1 lakh of this system. Various applications, immediate applications. Nowadays, the water pumping system, these are used in household irrigation. Okay, these are irrigation system. Okay, drinking water supply to the household. Then swimming pool, this is swimming pool, and then fountain. Okay, and water supply in the industry. These are the applications of solar water pumping system. These are immediate applications. Now, the potential application, long-term application may be in railways, water pumping, okay, in defense system, that may be in airline, right? These are the long-term applications. So, we have considered this standalone system till now. Okay, standalone means the solar array was not connected to any utility grid. That was generating some power, and that power was used to feed the local load, like local one. Let's say we have installed some motor pumps for our field, 5 kilowatt or 10 kilowatt. Okay, so that will be for that motor pump only. Now we can go for the microgrid system, we can say, and that is the configuration of grid interactive solar PV powered BLDC motor driven water pump. So it is called grid interactive because there is an interaction of solar array with the grid. Okay, with the grid. Right. So here there is a BLDC motor which is used for water pumping. Okay, obviously. Here this is solar PV array. This is the boost converter which is used for maximum power point trading. This is voltage source motor. Okay, and this is single phase grid. That can be 3 phase grid also. As per the availability. This can be 3 phase. But here we have taken the single phase grid, and this is the single phase voltage source converter. So this is actually the bidirectional converter. That's why we are writing converter, not inverter. Inverter means DC to AC. But when we write converter means it can be AC to DC, it can be DC to AC. Bidirectional. That is single phase voltage source converter. That means this PV array power can be fed to these grids. Sometimes we may not need water pumping. Okay, we may not need. So how we will utilize our solar power? In that case, what we will do? We will transfer the power generated from the PV array to the grid. Okay, that will give full utilization of solar water pumping system. And sometimes, let's say during night, this power, this PV array will not generate any power. How we will operate our water pump? In that case, this water pump will take power from the utility grid. That means sometimes this grid will be supplying power, and sometimes this grid will be drawing power. Okay, so that's why it is a bi-directional control. This is taking power, as well as this is drawing power, depending upon the weather condition and depending upon the requirement. So actually what happens when there is full radiation and optimum temperature, means when this solar PV array is able to generate full power, there will be no use of grid. Okay, all the power will be taken from the solar PV array because it is able to generate full power. But during morning, it is not able to generate full power, so remaining power will be taken from the grid. Okay, so required power by this load will be shared by PV array and grid. The contribution of PV array and grid. In that way, we can achieve this control. So this is single phase grid here. This is single phase voltage source converter, and to control this single phase voltage source converter, we have to sense the source voltage. This is grid voltage, source voltage, and we have to sense the source current. Again, okay, and this is VDC. VDC is this one. DC voltage of the voltage source inverter. We have to maintain this DC voltage at constant, and we can generate the force switching pulses G1 to G4, because in single phase converter we have only force switching. Okay. And this is very simple logic for the control of this voltage source. We are sensing this voltage source, we are sensing the grid voltage Vs, and we are using the single phase PLL, that is phase lock loop. Through this phase lock loop, we can get angle theta, sin theta. Okay, and this is voltage regulator. This voltage regulator is used to control this DC bus voltage. Okay, because we have to maintain this DC bus voltage at constant. So this is the reference value of VDC, and this is the same value of VDC, and we have used this low pass filter to eliminate any ripple which is present in this DC bus voltage. These two voltages are compared, and using the voltage regulator, we have maintained this DC bus voltage. So output of the voltage regulator will be the peak value of source current. Okay, ISP. P means peak. So peak value of source current we will get from this voltage regulator. This peak current will be multiplied with sin theta. So when we multiply the amplitude with the sin theta, this will become what? This will become the waveform of source current, IS sin theta. So this is the waveform of source current, IS reference. The waveform of the source current will be compared with the actual source current, because we are sensing the source current through the current sensor. This is the source current or grid current. Okay. So waveform is compared with the actual source current, and by controlling, we can generate G1 to G4. These are the four getting pulses. Okay, using this current control. So in this way, we can operate this voltage source converter. And this is bidirectional. Sometimes power will be, sometimes current will be in this direction, right to left. Sometimes it will be left to right. Any question for discussion? We can discuss there, we can go ahead. If there is any question.
Participant can ask how DC-DC converter is helping the system to get the maximum power tracking. How DC-DC converter is helping.
So we can explain from this diagram also. Here we can see there is a DC-DC boost converter here, which is connected across this PV array. So actually, we want to obtain the maximum power point of this solar array. So how we can obtain? We have to compare some signals like voltage of PV array and current of PV array. And when we want to implement some control logic, control logic cannot work independently. That must need some power electronics control. Then only this control logic can be implemented. Here also we can see this is the control logic, and to implement that control logic, we have used this power electronic control. Similarly, for the speed control logic, we have used this power electronic control. So similarly, for maximum power point tracking control, we have to use some power electronic control, which may be DC-DC push converter. This may be any converter. This is not just a DC-DC converter. Here we have used DC-DC, but we have seen in the previous topology, this was also used for MPPT. So we have to use at least one converter, that may be DC to AC, AC to DC, or anything to implement this control, MPPT control. So for simplicity, we have used boost converter, otherwise we can use buck converter, we can use buck boost, or any advanced converter which are available. So that is the role of this DC-DC converter. The role of this converter is only to achieve MPPT. There is one switch, at least one switch is required in converter. There may be multiple switches. Some converters have more than one switches. Okay. Some converters are interlinked converters, some converters are isolated converters. There are so many converters. At least one converter could be used to implement the control logic. Because through control logic, you will generate some pulse. Okay, and that pulses will be used to operate the switches of this converter. So that is the role of DC-DC converter here in this topology. But we can, yes, we have seen previous topology, we can eliminate this and we can achieve MPPT through this converter. So we need at least one converter for the control implementation.
It is, can we say that we are using the PV's array and it is producing the DC power? That's why we are using the DC converter. Or if there is AC power, we can use the AC converter, AC converter, something like that.
Power is not AC or DC. Power is just power. It may be mechanical power, it may be electrical power, it may be thermal power. Power is not AC or DC. We just say 2 kilowatt, 3 kilowatt. It will be AC system or it may be DC system. So here, if you use DC to AC converter, that will also work for MPPT. It will give some power. It is giving constant DC voltage. It is giving DC current. Okay, and power is multiplication of voltage and current. So it is giving some power. It may be, it is DC source, that's why we are saying that it is giving DC power. If it is, let's say this grid. So this will give AC power. We can say this will give AC power. But power is not AC or DC. This is just a source actually. So this is, you can use AC, sorry, DC to AC you can use. You cannot use AC to AC.
DC to AC.
DC to AC you can use because voltage is actually DC. Current is also DC.
And what is the Hall sensor? The Hall sensor is something different from the voltage or current sensor. It has unique features of Hall sensor that they use here.
Hall sensor is actually using the Hall effect concept. Hall effect concept. Okay, we know Hall effect. What is Hall effect? So the Hall effect is common, and that concept is used for current sensor also. That is used for voltage sensor. So voltage sensor as well as the current sensor, both are Hall sensor. Both are Hall sensor. Similarly, the position sensors are also Hall sensor, but that are actually the mechanical position sensor. But this voltage sensor, this current sensor, these are actually the electrical voltage sensor.
And then the last question is, in the slide 28, you have used the 1/Z block. I think unit delay.
28.
So what is the purpose of using that unit delay block, and what is?
Yes, 28. Yeah.
What is the purpose of using this block?
So I am coming to the MPPT logic. 1/Z is actually delay. Okay. So here you see, we need VPV, IPV, VP0 and IPV0, right? And we need DVPV, delta VPV, that is VPV minus VP0. So how we will get DPV0? 0 means previous signal. This VPV is current signal, 0 is just a previous signal. So how we will obtain this previous signal? Using the delay. When we use delay means that will give you previous signal. Okay, so that's why we have used this delay. Previous signal is just before the one sample time. Just before one sample time.
Any more? Sir, based on this model, if you change the motto to, let's say, synchronous reluctance motto, because initially said this motto is expensive. So if you change the motto, we have to do some modification or restore the same motto.
Then we have to change the entire control logic. For each motor, the control system is different. The speed control system is entirely different for each motor. Okay, we may have to change the converter system. Here we have used this voltage source inverter. This may be changed. It depends on the motor actually. And this control logic will also be entirely changed. Okay, so it depends on the type of motor actually. Like for induction motor, we use vector control. Okay, then TOC. So likewise for the BLDC motor also, there are so many different controls. So these controls will not be applicable for any other motor. This is especially for BLDC motor. Now, if you use SYRM, that is synchronous reluctance motor, there are some dedicated control system for that motor, especially. And that control may not be used for other motor. So that depends on the motor actually. Some part may be common. Some part may the switching pulse there. This should be common for all because there is some forward converter which needs some switching pulse. So that part will be common. Some part may be common, but entirely that may not be changed. That will be different.
So, sir, why did you choose this motto?
This BLDC motor.
Yes, sir.
That I mentioned here that the efficiency wise this BLDC motor is very good. It has more than 92% efficiency, and this motor is being used nowadays in many applications like electric vehicles, in water pumping system, and small power, like you can see the hard disk, okay, your cooling system, fans. So there is practical proof of this motor actually, but we don't have any practical proof of SYR. These are in research case. But I am saying that this motor will be better for India because we don't have permanent magnet in India. We are dependent on China, so we cannot manufacture. But we can manufacture this SYR. So in future, this SYR will definitely replace this permanent magnet in case of India. Because these are good motors, SYR and SYR. These are good motors.
Yes.
From the first approach, one of the things that you eliminated was the voltage center. Now, in the second approach, how do you protect the motor from the output of the BSI without having eliminated the current in the circuit?
These current sensors are eliminated, right?
Yeah.
So as I mentioned, that when you eliminate this, actually this sensing of these current sensors are required to protect the switches from overcurrent or short circuit. But when you don't use this current sensor, you cannot protect this inverter from overcurrent or short circuit. But only what you can get is you can reduce the cost, but the system will not be reliable. Okay, reliability will be compromised. Now, you can sense this current, but we don't need to use this current in the control logic. There are two things. You are sensing this current and you are using this sensing in the control logic, just like this. In this topology, you can see these currents are used in this control logic. Okay. So there will be a two control loops. Outer loop will be a speed control loop and inner loop will be current control, just like this. Another way is we will sense this current, but we will not use this current in control logic. We will sense this current only for the protection, not for the control. So in this topology, what we may do here, we have eliminated this current sensor for the control, but we will sense this current and use this current for the protection of the inverter. Protection only. We will not use this current in control. So there are two ways. You can use this current sensing for control, or you can use this current signal for protection only. But to increase the reliability, we should sense this current just for the protection. We will not use this current for the control, but we will sense this current for protection of the inverter. from the short circuit and overcurrent. Then we can make a very reliable system. And we can increase the life of the overall system. We can give the warranty of 5 years or 10 years.
One more. So can we directly connect to the grid and
Grid
from inverter 3-phase VSI to the grid in single step? We will not connect VLDC motor. We will directly feed solar power to the grid.
Yes.
Using VLDC. This control approach is valid for that.
If we have not BLDC motor, then we don't need this BLDC motor control. Then we need some grid side control, and we have to take care of power quality improvement like that. Just like the simple microgrid. Okay, we will just use this PV array. If you see this diagram here, if you remove this BLDC motor part, here if you remove this BLDC motor part, then this will become a simple system with PV array which is feeding this grid.
Yeah, this is feeding through the DC to AC, AC to DC. Through this one. No, I want to know that about 3-phase VSI. Is it able to feed the solar power to the 3-phase
Grid.
Yeah.
Then we should have a 3-phase grid here.
Yeah. Is this able to feed?
Yes, we should have a 3-phase grid here. Then this part is not required. And there will be 3-phase grid, there will be no BLDC power. Then this control logic will be changed.
Okay. Control logic.
Control logic will be changed. This BLDC motor control will not be used. Speed control will not be used. This control will be used because this is grid side control. So this control will be applicable for grid feeding. Here, this controller is for grid feeding for single phase. If you use 3-phase grid, then this control will be modified for 3-phase.
Good. I was thinking that the boost converter is there to magnify the DC voltage so that we use small number of PV cells. But you are saying that the boost converter is not there for that purpose. This is
Yes. So, the boost, actually, basic characteristics of boost converter is what? It is used to increase the voltage level. When you use buck converter here, then that will decrease the voltage level. Our objective is not the voltage or current. Our objective is power. What we want, the power of the wire should be maximum. Okay. So we can use any converter, boost converter or buck converter. All the converters can be used for maximum power. We just need only one switch. So boost converter also has one switch, buck converter also has one switch. Similarly, buck boost converter also has one switch. So we need only switch. Converter may be anything. We can attain the MPP. Our objective is not here to increase the voltage level or decrease the voltage. If I want to increase the voltage level, then I will connect so many number of modules in series. If I want to increase the current, then I will connect so many number of modules in parallel. So basic objective is not to increase the voltage here. Basic objective is just to provide MPPT. Right? We can use buck converter also. There is no problem. Only benefit when you use boost converter here, this inductor on the input side. So this inductor will actually help in reducing the ripple on this PV current. Okay, PV current will have some ripple. So this inductor can actually act as a filter because it is connected at the input. So that will act as a filter and it will try to smooth the PV current. That is the another benefit of using this boost converter. When you use buck converter, then at least in the place of inductor, what will be there? Switch. Okay, in place of inductor, that will be switch. That will cause a very high ripple in the current. So when we use boost converter, that will give additional benefit. Any other point for discussion?
You have discussed about BLDC motor. So, is there required to discuss THD?
THD. So in grid connection,
No. In highlighted case,
standalone. Okay, so in standalone mode, we have only one loop, that is BLDC motor and water. So we actually THD means when we connect the system with the grid, then actually as per the IEEE requirement, the level of THD of the source current should be within permissible value. But when we have some standalone load, we have only my load. So I am operating my load, I am not disturbing the load of any other. So nobody has objection that how I am operating my load. And if you calculate the THD of this BLDC motor current, BLDC motor current is actually quasi square wave. If you see the waveform, so quasi square wave of the THD of around 31%. And you know, so 31% will be the THD of the BLDC motor current, and we don't want to reduce that THD. If I want to reduce the THD, then let's say below 5%, the waveform will become sinusoidal. But BLDC want quasi square waveform. That is the desired characteristic, that the voltage should be trapezoidal and current should be quasi square. That pattern should not be disturbed actually. If that pattern is disturbed, then BLDC motor will not be operated properly. So we don't want to reduce the THD. Actually, there is no point of THD in that. Because our load is fixed, that needs quasi square current and trapezoidal voltage that we are getting. So we are getting correct waveform, quasi square and trapezoidal voltage. THD is of course less if we talk about IEEE recommendations and IEEE standard. But here there is no point of THD because this is just fitting our local load. When we connect this system now in this topology, there will be a point of THD because we have not now connected this complete system with the grid. Now we will talk about THD here because it is connected with the grid. So the grid current THD should be less than 5% as per IEEE standard, and voltage should also be perfectly sinusoidal. But this motor side current, the motor side voltage, it should be trapezoidal voltage and quasi square current. THD will be this side only, grid side.
In the VSI, because of the continuous firing of the the switching, is there a possibility of adding more
Harmonics. In this system or standalone? In VSI, when this is standalone system, so is there any chance of harmonics? Harmonics, this will generate, as I said that there will be trapezoidal, means obviously this will have some harmonic. Sinusoidal is harmonic free. Any waveform which is not sinusoidal has some harmonic. So obviously it will have some harmonic because it is providing trapezoidal waveform. But that is desired. That is not actually unwanted. That is desired. Trapezoidal is desired. That is not unwanted signal. So obviously this VSI will generate trapezoidal waveform which will have some harmonic, but that is actually desired.
I forgot to say that on one page, we were talking about the duty cycle, which is 1. And I think when duty cycle is 1, there cannot be any output because we need a duty cycle to control the switches. So how can we have a duty cycle of 1?
Here, when the radiation is 1000 watt per meter square, this duty cycle is 1. 1, because the FDP will generate this duty cycle corresponding to 1000 watt per meter square. Now, when we compare this one here using the comparator, you can see the comparator above. You can see here also, and you can see here also. Here. Okay, let's say this duty cycle is 1. We are comparing this constant value 1 with this high frequency sawtooth carrier wave. Okay, when we compare this with the one, what we will get at the output of this comparator?
The same as the sawtooth carrier wave.
Sawtooth carrier wave. At the output of comparator. What you will get when you compare this, actually this is sawtooth carrier, okay, and amplitude of the sawtooth carrier is 1, so it will be varying from 0 to 1, okay, 0 to 1, 0 to 1. This is the first input. Another input is constant 1. So when you compare this constant one with these, what you will get? One. Constant one. Okay. This you will get constant one. At this time we are getting this pulse. So when we use this analogy, first input is one and second input is just waveform. And the output you will get one or two. This waveform. Right? So this waveform we will get which is low frequency waveform because duty cycle is one. But when the duty cycle is not one, let's say 0.7, then at the output of this comparator, what you will get? This kind of pulse, high frequency pulse. So this high frequency pulse will be combined using this analogy with this low frequency pulse. So ultimately you will get this pulse high frequency. So when the duty cycle is one, at the output of AND gate also, we will get this low frequency pulse. But when the duty cycle is less than one, at the output of AND gate, we will get high frequency pulse. So that is explained in this waveform also. Here, the duty cycle is one, right? So switching pulse is harmonic free. There is no high frequency component. But when the duty cycle is, you can see 0.7. So you can see the switching signal. There is high frequency component because duty cycle is less than one, and that is also reflected on the waveform, current waveform.
Okay, so time is already 4:30.
4:30.
Yes, sir.
May take last 5 minutes just for the grid connected system. This system. Right? So here, as I explained that there will be bidirectional power flow. Sometimes it will take power, and sometimes power will be drawn from the grid. This is the control logic. We will see some experimental results. So initially what happens, SPV array is feeding from, means we are getting full power from the PV array and full power is fed to the motor pump. Then next condition is SPV array and grid feeding from. Means initially the radiation is 1000 watts per meter square, but after some time radiation is now reduced. So in order to get the full amount of water, some power should be drawn from the grid and some power from the PV array. Both sources should contribute. That's why initially you can say PV array power is 1450 or 1500 watts, and now PV array power is reduced. Initially grid current is zero. Why? Because PV array generating full power, whatever is required, grid current is zero. But at this point, PV array power is reduced, so some power is taken from the grid. That's why this is the grid current, which is to be drawn by the load. So load is drawing some grid current. Okay, this is IA, and this is the ISA, that is the stator current. So you can see ISA is constant throughout the operation. Means motor is always running at full load. And this is the speed. So this is the speed at 3000 RPM and the steady state, and this is continuously running at 3000 RPM. Even the solar radiation is reduced because motor is taking remaining power from the grid. Okay, you can see this 1 kilowatt per meter square operation. This is the power, and the radiation is reduced to 400 watt per meter square. So power is only 550 watt. PV is giving only 550 watt. The remaining power is provided by the grid. Next condition is when only utility grid fit PLC motor. Means this is the condition of night time. At night time, PV array power is zero completely. So all the power must be drawn from the grid only. Now there is the power quality factor, like total harmonic distortion, power factor. This will come into the picture because now there is a grid and there is a load. So you can see this is the sinusoidal current. Okay. So through this control, power quality is improved so that the PHD is as per the IEEE standard and power factor is almost unity. You can see this is almost sinusoidal grid current. Sorry, this is grid voltage. VS. This is the grid current. Okay, and this is the motor current, and this is the speed 3000 RPM. So you can see the total harmonic distortion here. This is the voltage. This is the scale down prototype. So voltage is 180 volt. RMS voltage is 180 volt. Okay, and this is the THD. You can see here. This is the power, grid power, Okay, 1.46 kilowatt is drawing from the grid. CNG is 2.9%. Okay, which is as per the hydrological standard. Next condition is STVRA and grid feeding pump. Both the sources are feeding the pump. After that, STVRA feeding it. So initially, both the sources are feeding the pump. After that, there is a condition that we don't need water pumping now. So what should be there? The PVRA should feed the grid now, right? So initially you can see the current is in phase with the voltage. Now after this you can see current is out of phase. So this represents the direction of power flow is reversed. Okay, direction of power flow is reversed. Initially power was flowing from grid to the motor pump. Now power is flowing from source PV to grid. So direction of current in the grid is reduced, change here. That's why the phase is now 180 degree. Phase difference between the voltage and current. You can see the DC voltage is maintained constant. You can see. And you can see this is the stator current. At this point, there is no requirement of water pumping, so stator current is now zero. Because motor is not running at all. Right? So, in conclusion, we can say that solar water pumping is interesting research area where a low cost and reliable solution is always desired. The proposed approach is justified by experimental results. The elimination of Hall effect position sensors makes the solar water pumping reliable, especially for submersible water pumping. DC-DC converterless, which is also called single stage approach, with position sensor with control. DC motor, this gives the best solution for water pumping. Okay, we are getting improved efficiency. We are also increasing the reliability. Thank you. Any other question?
So all participants already have their asked question. So time is also over. So this assessment is waiting for us. Yes. Thank you, sir. Thank you so much.